Hi, my name's John Weber with Schneider Electric. We're going to be talking about DC coupled systems today and leveraging the energy storage that you have on site along with solar or other renewable sources, including microhydro, as well as wind. What we're going to be covering today's presentation is talking about exactly what a PV system is, because there's several different types, AC coupled, DC coupled, as well as just straight grid tie, as well as exactly where DC coupled systems really shine within a solution, how we can use that energy storage to consume power on site, as well as leverage what's already there for a backup system, so creating AC power when the grid goes down to keep the lights on, as well as once we've chosen that system, how do we know that it's the right solution? And then, of course, the big question is energy storage, and how do we bring in the right amount of storage, and what's the right depth of discharge? There's a lot of things to cover within energy storage choices. And then finally, once everything's put together, installed, how do we make sure that system is running well? And how do we make sure that we're keeping up with seasonal changes as well? Schneider Electric takes your safety very, very seriously. So please, when you're working with our equipment, take the time to look through the first few pages of the manual where it does cover the safety warnings. There are some things that are different between each product. If it's a grid tie inverter versus a off-grid or battery-based solution, you may want to make sure that you understand exactly what some of the differences are between those installs and taking the safety in account. So what is the real difference between choosing a grid-tied system, AC coupled and DC coupled solution? We'll kind of cover the next few slides, really diving into exactly what those differences are and helping make the decision what's going to be the best choice for the needs of the solution on site. So what exactly is a grid-tied system? This is a solution that depends on an AC source to produce power. It won't work when that AC source isn't there. In essence, what it's doing is it's injecting current onto a sine wave. It is one of the most efficient ways of doing DC to AC conversion, but unfortunately, if it has a location where the grid is going to be inconsistent or frequent brownouts, that can create a situation where the system kicks offline and has to requalify an AC source. Where this system typically shines the best is when you have consumption during the day or during peak solar hours, and you're trying to get the most out of that solution and not too concerned about having a backup or having that system work when the grid goes down. So next up would be our AC coupled solution. And the reason that somebody may want to do an AC coupled solution, and very typically, is that a grid tie solution already exists there, and you're wanting to add energy storage to that solution. So it continues to work during a power outage, and you can charge the batteries during a power outage with that AC coupling. It does sometimes require some advanced control solutions to manage that power so we don't accidentally overcharge those batteries. When we talk about not working with a generator, you're going to have to put in a switch of some sort so that we don't ever accidentally, if the generator's running, sell power from the grid tie inverters onto that generator. Some very bad things can happen there. So typically what happens is that if the generator's called to start up, that also just simply opens up or disconnects the grid tie solution as it's coming in, and that allows us to then charge off a generator, but then go back to the renewable source if it happens to come back. Also, it is a very efficient use of solar, again, if that consumption is during the daytime use, which is why a retrofit makes a lot of sense. If you're trying to use it on a daily cycling application, of course, we're passing through this DC-based inverter twice, and so that can create some inefficiencies there when we compare it to just straight DC coupling. And of course, there's a lot of extra material here that adds cost, and so if you're trying to choose between DC coupling and AC coupling to start out with, unless those loads are coming in during daytime hours, DC coupling really makes the most sense because it does give you the most control and versatility over a total solution, and adding something like a secondary AC source of a generator can make it quite easy. With all things in life, of course, there's some give and take. When we look at DC coupled solution, it does allow for the best control over our solar production. Because we have the battery bank, which kind of acts as an energy sink, if you will, the system knows exactly how much storage we have, and based on the voltage, the charge controller react if the inverter, in this case with the Connect SW, goes into a load support, or if the batteries are already full and it starts producing power for a load, then of course the charge controllers will begin to increase the amount of power that they're producing into it. So it's a nearly 1-to-1 ratio with those. Generators are a pretty easy thing to add to a solution like this because we do have control over that battery bank, and we don't have to worry about with AC coupling power being pushed back onto it. Makes for a really nice solution. Of course, the give and take of it is that if we have daytime consumption and that's our primary consumption, again, grid tie or maybe AC coupling could be the best solution. But for a true cycling application where we're asking for energy 24/7, then DC coupling is where it really starts to shine as a total solar solution. Especially with things like self-consumption, where we're choosing to try to use the solar production, even during the daytime, over the grid, we can actually inject current because the inverter itself actually knows what's passing through it. And with some settings within the Connect SW, we can inject current into that. And that's pretty much called load support. So we can get the best of both worlds with consuming power 24/7, as well as bringing in a reasonably sized generator so that we can use as much of that system as possible. With DC coupling, of course, that one next step is again, it's a very versatile solution, and if we're trying to support that power for 24/7, this is the ideal solution. We have that direct control again over the battery voltage, and we have that communication between these Schneider Electric charge controller, that be the MPPT 60 or the MPPT 80, communicating over ZAN bus to the system. And of course, this is what allows us to be independent of the grid and even continues to work when the grid goes down. The other nice thing is that if we do bring other DC charging technologies in, say wind or micro hydro, as long as those units have a high set point, they're trying to bring the batteries up to 14.4 volts, or on a 48 volt system, 57 or maybe 58 volts maximum, it really makes for a nice solution because we can continue to use that power because the inverter itself doesn't really care. It just sees the battery bank and provides that power to it. And of course, again, with generator support, we're able to inject current on a reasonably sized generator, so we don't have to bring some monster in there that's sized for just that one big load. So if a big inductive load comes on, gosh, we got a size for that one load. Instead, we can kind of size for the nominal loads plus charging and allow the inverter to step in and actually support a smaller generator when a very large load comes on. In particular, we talk about inductive loads. So where within in the world does DC coupling really makes the most sense? The nice thing with this solution is that it continues producing async power, of course, when the grid goes down. But one step beyond that is that we can actually set the system up to be kind of picky when it comes to choosing power. And when we get into brownout situations, of course, we can say that enough is enough and disconnect from that source, saying that it's unqualified. And the really nice thing about that is brownout conditions can be very, very hard on certain electronics. And this will allow us to qualify that source and then disqualify that source once the a brownout condition occurs. And then of course, once the brownout condition goes away and we have some decent power, then we can simply reconnect to that AC source, begin charging, filling those batteries up, and from the power output side, we have nearly uninterrupted power throughout that. So again, regions where grid power is inconsistent or very, very dirty, as well as if regions where price for power is very, very high, with the example that I've been using, which is the Connect SW, we can't sell power back to the grid, but sometimes that's a good thing because places like Jamaica, actually you spin the meter forward if you accidentally sell power back. So we want to make sure that when you're choosing an inverter and you're choosing the setup for that programming, we'll be going on to talk about the Connect XW next, but if you do grid tie, sell in a region where it's unfriendly, bad things can happen from the power company getting mad at you or just spinning that meter forward when you thought that you'd be spinning that meter backwards. That's where that load support comes in and where we can inject current on the output of the inverter. And, for the primary loads that are on that load panel, we're continuing to offset that consumption. So the XW Plus and leveraging energy storage. This is probably one of the best solutions for inverters that are battery-based out there in the world. And the reason that I say that is that the XW is a very versatile product. It can do backup power with very, very fast switching time. And again, qualify that AC source. And if it says, we're in brownout conditions, gosh, let's go ahead and disconnect. Along with that, the XW Plus can also do some of the similar things we talked about with the connects to SW, which is load support and reducing that consumption. And so if power prices are getting into the 30 or 40 cents a kilowatt hour, and that's US prices, then this is a system that's going to be a whole home solution for places like in the IEC. And so let's go ahead and talk about a little bit more on the IEC. So the IEC with the Connect SW, of course, we have a 60 amp pass-through. So if you have a 50 amp home main panel, this is a great opportunity to do basically what we call a supply side tap, if you will, where we're putting the inverter and the solar solution between the grid and the main panel. This is going to allow us to see absolutely every single load inside the home and be able to either pass power through to the grid or inject current onto it with a load support. Of course, ideally, if we can set this system up, we're only going to use the grid if we have exceptionally large loads, and we're only going to use that, if we have a large inductive load or something like that. But beyond that, our goal is to actually stop the meter. And the charge controller, of course, is going to react by injecting extra current. So if the batteries are full, the system's in pass-through, and then load support comes in, we're able to actually have the solar charge controller begin injecting more current onto the batteries as the inverter draws it out. So again, that one-to-one idea and holding that main panel. Of course, if you add a transfer switch to that system, we can actually choose to disconnect from the grid completely, and you can control through a timer or something like that when that would occur. Of course, the nice thing with this solution as well, the XW Plus has two AC inputs, unlike the Connect SW. So it has an internal transfer switch for managing power from the grid or from the generator. So if the grid's not there during extended power outage and you want to bring a generator into the solution, very easy to do. Bring that generator in with load support. The Connect SW knows that it's got a secondary source, and you can custom program that system so that it acts differently, knowing that there's a generator as the AC input versus the grid. So charge controllers. This is something where within the Schneider electric product line, you have two really nice choices. With the MPPT 60, it allows adding secondary or third strings of solar to an MPPT 60 fairly easy. What I like about it compared to some of the other products that are out there on the market is it is passively cooled. So it is a completely silent operation, and it truly is a standalone solution. So you don't need really any extra equipment beyond the MPPT 60. So just kind of step outside of a DC coupled solution where we're using an inverter with the MPPT 60 because you can program it right there on site. If you're adding it to an existing solution outside of the Schneider electric product line, very easy to do. With the MPPT 80, this is a very unique product in that it has a 600 volt string inverter allowance. So we can build these very, very large strings, which is going to reduce the overall cost of the solution. The MPPT 80 in comparison does cost a little bit more, but then when you're taking out the balance of systems that would be required for something like the MPPT 60, and as well, because if you have longer distances to run, the cable sizing starts to go up. The MPPT 80, where you've got it set, at 500, 550 volts nominal, then you can use very small conductors within that solution compared to the 60. So what you would have spent on the 60 price-wise compared to the MPPT 80, those two kind of become one-to-one or even when we start looking at the fact that the MPPT 80 can definitely bring down costs in the balance of systems around it. And then finally, the MPPT 80 is a little more efficient on overnight consumption. We're talking a few watts here, but it's worth mentioning that the MPPT 80 does consume just a little bit less power to keep itself going and ready to go for the next morning. For a lot of places in the world, the Connext SW is a very nice choice. Because we have integrated switchgear for it, it makes bringing the solution together very, very easy, and you can use the knockouts to give yourself a display along with the comm box to be able to see that system through Insight from anywhere in the world. It is the most value add system that's out there for battery backup or an off-grid solution. Of course, it is 50-60 hertz switchable, and we have a 230 and 120/240 solution. Another nice thing that's worth noting about this system is that it can take a 120 input and produce 240 output. So it reduces some of that cost when we start looking at things like autoformers, if you're going to need that or not. With the Connext SW, of course, at its heart, it is a DC to AC power supply that produces a pure sine wave. It is also an inverter charger, so it can take power from an AC source and charge those batteries. And again, compared to a lot of other solutions out there from competitors, and maybe even compared to the XW Plus, if you're looking for a smaller size solution, this is definitely the most cost-effective way of bringing in a pure sine product into this, as well as with some of the pre-wired options that we have with our load panels. You can bring the solution together very, very quickly and very, very easily. So continuing the same idea when we talk about residential self-consumption with DC coupled solar, we have a lot of different ways that we can leverage using that solar. In particular with the Connext SW, of course, just simple battery backup is very, very easily done. You simply move the circuits that are important for backup from a main panel out to a AC sub panel for those residential loads. Of course, AC support and enhanced AC support mode allows the inverter to use the batteries and then make sure that the batteries are completely charged before using them again. A lot of manufacturers don't take that into account. And so if you don't have prime solar days, day after day, you can end up discharging the batteries and leaving them in a partial state of charge, which over time can reduce their battery life. Of course, finally, when we talk about peak load shave, these are areas where especially you have something like tiered pricing and you want to set up timers within the solution to actually begin load shaving at certain periods of time. Usually here, like in North America, we're looking at times somewhere between 4 p.m. and 10 p.m. Usually that's when, of course, people get home and air conditioners come on, ovens come on, and a lot of consumption occurs during that time. And so by setting up timers, we can make sure that the PV charges those batteries and sets the system up ready to go. And then once that timer is hit, we simply start injecting current and cut that consumption during those peak times down, and therefore we are peak load shaving. So how much storage is really needed for these different types of applications? Of course, with backup power, we need to understand the loads that have been moved from the main panel over to the secondary load panel that are going to be backed up during that power outage. Understanding the behavior of the client, especially if we're going to be allowing just standard plugins to be used, which is common, but are they going to start plugging things in, especially convenience items that can be high consumption, anything from a coffee maker to hair dryer, those are convenience items, and understanding if the client's willing to move those around can change the size of the battery bank. Of course, education is probably the most important thing that can be done to set expectations. So when setting up energy storage, are we looking at a 12-hour power outage or are we looking at a full 24 power outage? And when we set those times, we're talking about not having any available solar there. So if we take into account that on a 12-hour power outage, within the next 12 hours, let's say the power goes out at 6 p.m., 6 a.m. rolls around, the batteries are going to be exceptionally low, but within a short period of time, the solar is going to come in and start injecting current onto those batteries and start charging them up. So typically somewhere between 12 and 24 hours is the right size for sizing that system out, because we can take charging into account. Of course, If the system starts to get quite large, you may have to start kind of balancing the idea of bringing in a generator to supplement power, because a natural gas generator can be a really nice way if somebody's saying, I need 3-4 weeks worth of backup, and here's the reasons why. You start looking at energy storage to guarantee those numbers, and it can get exceptionally large. Bringing in a generator can alleviate that, and using an XW Plus along with it, because it has that dual AC inputs, makes for a really nice clean solution overall. So when we look at self-consumption, we have a couple different ways that we can use that self-consumption. If really the primary use for using energy storage is backup power, we can set that self-consumption for a float voltage on the batteries, which simply means that if the batteries are full, then there is extra solar. We can actually produce power to offset the consumption with inside the home without dipping into those batteries. The second way that we can attack that self-consumption model, of course, is allowing ourselves to dip into those batteries on a daily basis, understanding that, we're going to need solar to recharge those batteries. And so it is current-based on the amount of current that we want to support passing through that inverter. So what we're self-consuming in this site is really the loads that are on the AC output of the inverter. So take that into account as well. The inverter is only aware of what's on its output. So if you only put a very small amount of backup onto there, then the self-consumption offset is going to be fairly small as well. The nice thing with this system is that we can pretty much guarantee that we're not going to dip too far into those batteries. Since we already have an AC source there and we're talking about self-consumption, the system's going to basically, once that state of charge has been hit, and injecting current onto that solution and just give it over to the grid. Of course, we need to make sure that the next day when that comes around that we actually have enough PV there as a significant charging source to both cover the loads on load support as well as provide charging, because once we get back up into a higher state of charge, the inverter is going to start covering loads. We need to continuously inject current onto that system so that we make sure that those batteries get charged up and are taken care of. Again, improperly programmed or sized, we can run into a situation where the system has been overtaxed and essentially those batteries are left in a partial state of charge day after day, which will reduce their life. So the kind of the two competing technologies that are out there right now, and yes, there are some others as well, but primarily there's a lot of talk about lithium ion storage and a lot of talk about, of course, the good old lead acid battery. Of course, there's two different technologies with lead acid battery. There's the sealed and the flooded versions of those batteries. But really, we talk about lead acid and how much we can discharge those batteries. The rules are going to hold the same between sealed or flooded. Lithium ion, of course, is very different and doesn't necessarily mind being in a partial state of charge. So deciding how the system is going to get used and whether or not to take into account the increased cost that comes with lithium ion and how the batteries are going to be discharged needs to be understood as well. So with lead acid batteries, of course, we want to make sure that we're not discharging those batteries below 50%. And ideally, really, we need to make sure that we're not going below 25, maybe at most 30% taken out of those batteries. So we have a remaining state of charge somewhere between 70 and 75%. Of course, with lithium, it's very different. And again, they can be used in a partial state of charge and charged and discharged. So if you're trying to decide which technology that's going to go in there, based on the needs of the site, you may find that lithium ion makes a lot of sense, just simply because you don't have to change parameters as often. We'll touch on that in a little while. The actual cost that comes with consuming power out of batteries needs to be taken into account when we look at what the ideal customer is. We can see here in the top of the slide that the cost of batteries, we're comparing kind of what if we put in twice as much storage compared to what is needed with a 50% depth of discharge, which we talked about in the previous slide. So everything being equal, 1,000 amp hours, 48 volts, and then we get the number of kilowatt hours of storage. The difference is the depth of discharge. So if we spent just $10,000 on a system, we can roughly expect around 2,000 cycles or a total life of about 48,000 kilowatt hours of storage out of those batteries. Of course, if we double that system in just the amount of lead that we're bringing into the solution and reduce that depth of discharge to 25%, the number of cycles more than doubles, and we get 120,000 kilowatt hours out of that system. So if we take that math into account, the number of cycles that we get down in the bottom right-hand corner, the cost and depth of discharge. So as the cost of the system rises because we are investing more lead into that original system, the amount of power that we're taking out each time reduces. And we get more cycles out of that system overall, and we get more than double what we'd expect to get. So at the end of the day, taking everything else into account, the cost at 10,000 is going to be about 20.8 cents a kilowatt hour to cycle those batteries at 50% depth of discharge. Whereas if we were able to double that battery bank and invest in $20,000 worth, or a 2,000 amp hour battery bank, the cost is around 16.8 cents per kilowatt hour. And you figure out the number of cycles that is, and suddenly that becomes a real number for cycling. And so please, really the point of this slide and what I want you to take away from this slide is that doing a 50% depth of discharge on a daily basis is not maximizing the value of the lead storage compared to a 25% removal of power, 25% depth of discharge each day. So if we're talking about self-consumption and using a DC coupled solution, one of the things that we have to take into account is the seasons. Batteries don't scale up well. So what we choose in the first place is kind of what we're stuck with throughout the life of the system. So adding additional storage after the first few months becomes unreasonable. And so we have to make sure that when we're using the system, especially for a self-consumption application, that we understand the summer season, we're just going to get simply more installation hours, and therefore we can guarantee that that system's going to get those batteries back up to 100% state of charge. Whereas maybe in the late fall, in the winter months, we just don't have as many hours of sun potentially. And so we have to change the programming to reflect that. So you decided that you do want to do a battery-based DC system. So let's talk about kind of what a real-world example of that system is going to look like. So this customer is residential. Currently, they're paying 42 cents a kilowatt hour. Summer hours is 8, winter is 3, and a yearly average is 5. So the grid can be unstable, especially in this imaginary world where we have storm seasons and they can lose power for a couple days at a time. So peak consumption in this model is between 5 and 9 p.m., and that customer is consuming about 10 kilowatt hours during that period. A peak single load is about 3.5 kW, but continuous is about 1.8. So when we're designing the system out and thinking about what we need for this example system, of course, we have to take some losses into account as well so that we can calculate the right amount of PV for that solution. So typically nameplate PV is, in reality, we lose about 25% D-rate on that. Charge controllers take about 2%. Of course, energy storage, because we are going to be cycling these batteries, is another 10%. The inverters are 92% efficient, so that means that we need to take about 8% into account. And then finally, of course, that wire sizing needs to be taken into account. So we take these numbers here and we multiply them all together, and we end up with a number of about 40% efficiency out of that system. So we need to make sure that the system's a little bit bigger, up to about 40%. Of course, depending on where the system's located, cold, sunny days can change that PV efficiency. But really the other numbers, battery charger, or the battery charge controller, energy storage, inverter, and wiring, those numbers aren't going to change too much. But the PVD rate can definitely be a number that changes depending on the location that it's going to go. So in this model, the number that we're looking at for 10 kilowatt hours with 5 sun hours on average, we're going to need about a 2 kW array. Take the inefficiencies into account, we multiply that number by 1.4, and we're going to need about a 2.8 kW solution to make this enough power for the system to work. So as an example system, Because we have about 58 amps, because we're working with a 2.8 kW solution, we can use either the MPPT 60 or the MPPT 80. Really, that comes down to how you end up configuring, either with multiple strings of panels or with the MPPT 80, we can possibly do a single string to wire that solution together. For inverters, we really do have that choice between the Connext XW Plus because it has that dual AC input. So if a generator is going to be part of that solution, the best and easiest way to bring that together, of course, being able to do grid tie, load support, and have some room to grow because the size of the system is just larger with the XW Plus. The Connext SW is the best value for this system. It does allow for a little more room to grow. You could arguably bring in a second charge controller without too much issue. And so it just comes down to really what you think that system is going to be used for now as well into the future. But for that example system, just moving forward, you can choose either direction to go, either the Connext SW or the XW Plus. For the example that I'm showing here, we're choosing the XW Plus, which this is the UL solution. I've chosen to go with the MPPT 60, partially because it allows me to just simply use the mini PDP load panel and be able to wire those charge controllers right in there. I am only going to need a single array with a combiner box up on the roof to run my final conductors down. Typically, when we're looking at standard over-the-counter panel, we're looking at an open circuit voltage of about 33 to 36 volts. That allows me to do 4 panels in series and 3 of those strings in parallel. Finally, the COM box to allow me to set up and configure the system as well as be able to see that system from anywhere in the world. The DC breakers for the charge controller, we have a 100 amp, 125 volt DC master pack, and then of course the 60 amp, 160 volt DC master pack is going to be the added pieces to this solution. So we've got it all installed and we're ready to see exactly how the system's going to behave. We can use the Connext Insight with the ComBox to be able to see that system from anywhere in the world and be able to see daily summaries as well. You know, one of the most important things that we can do when we're working with a battery-based solution is understanding exactly how that system's going to work when the power goes out. So again, education and setting expectations early is one of the most important things that we can do to help make sure that this system is going to go together correctly, and it's going to meet the expectations for the customer. Nothing worse than a disappointed customer along the way. This also allows us to see if there's any conflicting settings, checking for load support and whatnot, as well as just making sure that all the circuits that are part of the system or expect to be part of the system are in fact installed. So with the ComBox, we can actually go in and see the system, how power is flowing around there. And through that setup process, we'll be able to receive email reporting whether or not the system is got any errors or critical incidences. Also, we can make notes on the outside of the house, make sure that our production is flowing the correct direction. So if the system's been initiated and we're in load support, we should see that those numbers are moving a little bit slower on the counting for power coming in. Of course, we can also check battery voltage, make sure that the system's discharging the batteries at a rate that's expected. And as with the monitoring as well, looking at the historical data to ensure that those batteries are getting charged up each day and we're not leaving them in a partial state of charge. As we mentioned before, that can be critical when working with the lead-based solutions. Of course, the last thing is that we, again, and I can't reiterate this enough, we need to make sure that that customer understands exactly what's going to happen during a power outage. With the Connext Insight, we can see a system from anywhere in the world using the web interface. And the nice thing with Connext Insight, of course, is that we can see both decentralized grid tie sites using the Connext CL, which we really haven't talked about, but the battery-based solutions we can definitely differentiate. Just simply by looking at the system, we can see the Connext symbol, and there's a small battery symbol there up in the corner, and that's how we differentiate between those two. Of course, looking at this screen, we can see that there's one there near Tennessee that's having a bit of problems. We can easily, at a glance, look at a system and then dig into exactly what's happening there and make sure that we understand what's going on and whether or not we need to roll a truck. once we dig into this solution and see exactly the power that's moving around here, we have a very easy view. We can look at historical data as well from the week, month, year, or even the lifetime of the solution, see where that power is going for backup and off-grid solutions, go into the battery energy. So we'll go through a couple of these slides, just show you exactly what the system's capable of doing. It's pretty neat stuff. Let's go ahead and look at exactly what we can kind of interpret from some of the data that it's displayed through the Connext Insight. If we're looking at solar energy on a battery-based system when it's DC coupled, probably one of the best things to look at is whether or not our production is matching our consumption. Here we can see that we have the load output and the PV output displayed within the system. Load output being orange and the PV output being blue. We can see here that the load output is quite a bit more than the PV output, so we can expect that the battery voltage would be dropping, and that without an external source, eventually we're going to need to add some more power to the system, either through generator charging, or if we had a sizable battery bank, wait till the next day during that installation period. But if we see this time and again, especially if we go from the daily view out to the weekly view, and we're seeing these kind of numbers, definitely the system's going to need an alternate charging source, or perhaps it's time to upgrade the system to a larger array. In this example here, again, we can see the battery charge. We can also see PV input along with generator input. So we definitely have a mixture going on here within this solution as an example. But again, really the point of this is to show that we can choose exactly what we want to see here within the parameters of Insight. There in the top center, we can actually choose what we're going to be viewing along with which series of sources. So if it's gen input in one case or PV input as a whole in another. The versatility of Insight allows us to see and interpret the data as we need it and be able to display that in a way that is consumable both by ourselves as well as perhaps the customer to better explain the behaviors of the system and change their expectations, if you will. One of the things that I really do like about Insight is that we can actually capture how much generator power has been applied to the system. And this becomes important for a couple different reasons. One, if we're expecting to offset a certain amount of power each day using the generator, we can double check that. We can determine whether or not we need a large array moving forward. But we can also see the number of or the amount of run time that's needed for the system, and therefore we can interpret how much generator time we've had as a whole. So if we're doing maintenance every 600 hours or 1,000 hours, just depending, this is a very easy way to see how much generator time we're doing without having to read a meter perhaps on site, which sometimes that's all the generators offer. Well, thank you so much for attending and checking this webinar out through our YouTube channel. If you'd like to see live presentations of our webinar series, please join us by going to the Schneider Electric website and checking out the company events section. So under solar.schneider-electric.com, choose the company drop down and then choose events. You can see where we're going to be somewhere in the world for some training, perhaps on site like we are here shortly for Solar Power International, but as well just our monthly webinars that we're doing. You can also see that and sign up for those events as well. So thank you again and look forward to seeing you during our next presentation.